Hello, my name is Dina. I will present our work on deep learning micro project about salary prediction. The team members are Zhong, Khunsa, and myself. I will present the first part of our project. That means the presentation of the dataset and the pre-processing. Okay, so the goal is to predict if the salary of a person is greater than 50,000 a year or not. So here we have a binary classification task. We have more than 48,000 examples, and we have 15 features. We have categorical and numerical features. We have some missing values, so it concerns only 3 features. We will see more details later. And also we have an imbalanced target class. Here we just want to tell that we have to be careful when we choose, when we will interpret the quality, the accuracy of our model later. So now let's see our data set. Our data is here. So features are here. It's, for example, age, education, occupation, relationship, race, and so on. And our target class is here. So I told you about the missing value for 3 class, for 3 features. So it's in the work class. So missing value is encoded like that. A string of question mark here in work class. There are also missing value in occupation, so here, and missing value in a native country here. So what do we do with missing value? We have made the choice to keep them. So what happens if we keep them? So for work class, instead of having 8 unique values, we will have 9 unique values. So it's the same for occupation. Instead of 14 unique values, we will have 15, and for native country, we will have 42 unique values instead of 41. Okay, good. I will go back to my slide. So, neural networks need values between 0 and 1 for input. So first of all, we need to transform our categorical values into numerical values. For that, we used scikit-learn libraries. And also, we need to standardize our value. So for that, the goal is to have the mean, mu here equal to 0, and the variance S here equal to 1. Okay, so to summarize, we made the choice to keep the missing value. We are aware of the fact that we have an imbalanced target class, and we encoded our features between 0 and 1 and standardized them. Now we are ready for the next step.
Hello everyone, so my name is Khunsa Aslam, and I'm gonna explain further what we did. As my colleague has explained our work, like what are the inputs and what are the data set, what is the data set that we choose. So in this video I'm gonna explain further what are the network structure and the parameters that we used. Okay, so in our network we used a multi-layer perceptron, a 4-layered multi-layer perceptron. And as you can see from my slides that there are 4 layers. The first one is the linear one. This is the input layer, and then the linear 3 is the first hidden layer, and the second hidden layer, and third hidden layer, and the last linear 9 is the output layer. So you can also see the output shape of our neural network in each layer from this diagram. And from this table, and there are like in the number of parameters on each layer. You can see it has been reduced from the input to the main output layer. So total parameters we had like 19,586, and trainable, they're all trainable parameters and these things. Okay, moving on. Okay, these are our training dataset results. So we applied like 10 epochs on this simple 4-layered multi-layer perceptron model, and the loss in the first, as you can see from this table, in the first epoch the loss is 52%, and validation loss is 38%, and the validation accuracy is 89%. But as the time, with the more training, with more epochs, we figure out that our loss was reduced to 31%, and we were able to gain the accuracy of 91.64%. You can also see the graphs of our accuracy and the loss. The accuracy was low in of the training set in the start, but gradually it increases. But for the validation set, it was not that low as compared to training, obviously. So it's a gradual increase. That's a good thing. So still needs a work done in it, but this is a good result. And the loss, similarly, the loss of our 4-layered multi-layered perceptron, it decreases with the time, training loss and the validation loss. Okay, so the next thing I'm gonna explain is the why we should use the activation function in our neural network. We have used an activation function of a value. The reason of using that will be explained later. First I'm gonna explain why to use an activation function in a neural network at all. So I want you to imagine like a simple the function of a simple neuron is simple is the sum of the weight and the inputs that is coming plus the bias. Why? This is the function of simple neuron. So if we don't use an activation function to it, it will be just a multiplication, a matrix multiplication, or you can say a linear function of the input layers. So we can say that without an activation function, the output of each layer is a linear function. And similarly, then it won't even matter how many layers that we are using in a neural network if we don't use any activation function. So in order to generate some non-linearity in the output, we need to use an activation function, or else it will be like equivalent to the effect of a simple feed-forward network which has no hidden layer. Okay, so the next is like as you can see, I showed a graph here. As you can see, if there is a neural network on which there is no activation function, it's if we draw a 2D graph of that, it's simple straight lines, simple linear functions, 3 lines, as these are 3 neurons of A, B, and C. These are, as you can see, it's a simple linear structure. It's of like no use because it's a simple matrix
So we've explained the reason why we apply a activation function, why we should apply activation function in deep neural network, and now I'm going to describe each kind of activation function we've applied. We've applied ReLU over the output of each hidden layer because ReLU put weight of some neurons that are negative numbers to be 0, which will lead to the sparsity of network and reduce the interdependence of the parameters and the occurrence of overfitting. And we only use sigmoid before the output of neural network. This is to increase the non-linearity of neural network models and to map value of output layer to the interval of 0 to 1, which makes it possible to apply cross-entropy laws after the sigmoid function. And why we just apply it before output instead of applying it through all layers, because the derivative of sigmoid will cause problem of vanishing gradient immediately in course of backpropagation. And the loss function we've applied is binary cross entropy, which comes from the formula of the Kr divergence. The Kr divergence shows how much different B is from the perspective of A. And how can we explain the phenomenon of vanishing gradient? We have to explain the process of backpropagation. In backpropagation, we update weight and bias in each epoch by the gradient of weight and bias of each neuron of each layer to the loss. And we can see from the formula that to calculate the gradient, we have to take into multiplication of the derivative of all output of layers of which is after the current layer. And if we apply sigmoid function, the derivative, the multiplication of too many derivative of sigmoid function will cause the value of gradient to be 0. In this experiment, we've replaced the each ReLU function by sigmoid function, and we can see that the phenomenon of vanishing gradient immediately happen after several epochs. So in that case, we can't update the weight and the bias anymore, and the network cannot learn anything more.
Et ensuite, nous utilisons nos données pour tester les avantages et les inconvénients du réseau avec single hidden layer. Un des avantages est évident. Sa vitesse est relativement rapide. Mais selon l'article de Telekarski en 2016, nous pouvons simplifier une inégalité comme suit. Ce qui indique que les deux réseaux F et J ont la relation suivante. On a créé d'abord un réseau simple de 4 layers et 8 neurones. Après 20 itérations, on a sa précision de test environ 0,85. Ensuite, on a créé un réseau avec single layer J afin qu'il ait une précision similaire. Parce qu'il s'agit d'un réseau avec single layer, P' ici est égal à 1. Pour approximer F, N1 doit augmenter de façon exponentielle de t. Selon cette formule, lorsqu'on augmente le réseau de 4 layers à 8 layers, le réseau GX doit augmenter le nombre de neurones 4 fois. Donc c'est 16. C'est donc on va construire un réseau avec 4 couches au lieu d'une couche unique. Lorsqu'on a fait le test ci-dessus, nous avons constaté que le résultat obtenu par le réseau à 8 couches n'est pas aussi bon que celui du réseau à 4 couches. Nous avons donc suspecté que le gradient a disparu en raison de trop de couches. Afin d'étudier le problème de la disparition du gradient, on a créé un réseau à 20 couches. Et la fonction d'activation de chaque couche est sigmoïde. Nous constatons que le gradient moyen est tombé à 0 tout à coup au troisième cycle, lorsqu'on a changé toutes les fonctions d'activation en ReLU nous avons constaté que le gradient diminue lentement et ne tombe pas tout à coup à zéro. En plus de changer la fonction d'activation, nous avons de nombreuses méthodes pour résoudre ce problème, comme la normalisation par l'eau. Normaliser le signal de sortie X à une valeur moyenne de 0 et une variance de 1 pour assurer la stabilité du réseau. Les données sont divisées en petits lots pour la descente de gradient stochastique. Et lorsque chaque lot de données est transmis vers l'avant, la normalisation est effectuée sur chaque couche. Voici deux graphies gradient contre époque. La descente du gradient vers 0 est plus longue avec la normalisation par l'eau. Et voici le graphie I prédiction contre époque. On peut constater que le réseau est plus stable après avoir rejoint une couche PN. Nous avons plusieurs façons de résoudre le problème de la disparition de gradient, y compris le remplacement de la fonction d'activation et l'ajout de la couche PN que nous voulons voir. De plus, il existe des réseaux résiduels long short item memory et la régularisation nous permet de résoudre un problème similaire qui s'appelle exporting gradient. Et ensuite, nous étudions le réseau du point de vue de la théorie de l'information. On va calculer les informations mutuelles contre l'entrée et chaque couche.